Greetings! I promised that I would post a supplementary video about cross-validation, so here it is. So, similar to the last video that I posted, which was about precision, recall, etc., etc., I used the labor negotiations dataset, and I'm going to do that again for this video. So I have loaded it into Weka, and now if you go to the classify panel, again like last time, I'm going to run an experiment with J48. Now, this time in particular, I want to highlight the fact that I'm doing cross-validation. For now, I'm going to change it from a 10-fold cross-validation to 5, because that's how I'm going to explain it after the fact. So it could be 10 or 5. At the moment, you may not know what that refers to, but we're going to get to that. Okay, so we're set up to run this cross-validation. I'm going to click Start. Now it ran the experiment. And here's the result buffer. It's the same result buffer that we looked at yesterday when we were talking about precision recall, etc., etc. But now I want to highlight different things about this result buffer. So if you scroll up to the top, it gives you some information about how the experiment was run. And then it shows you a tree. Now, if you look at this tree in text form, it's a little bit confusing. If you right-click on the left-hand side where it lists in the result list the experiments that you have run, you can click to visualize the tree. And so we see here the tree that it gives you. Now, it's important to note we loaded a file on the front panel, and this tree you see was built on that whole data set. Not using cross-validation, but just training over that whole set. So it used that data to fit the form of a tree, and this was the best fitting tree. So that's the tree that it gives you as a result of the training, and after it trains that tree, then it does the cross-validation, and we set it up to do a 5-fold cross-validation, and the results from the cross-validation are the results that are presented at the bottom of the screen, and that's where we see accuracy, and we see the kappa, and we see these accuracy by class metrics, and we also see the confusion matrix. All of these are coming from the cross-validation. They don't involve this model that was trained on the whole set of data. Instead, they involve running this cross-validation. I'm going to show you what that cross-validation is and does, but I wanted you first to notice the output that you get from Weka. So in your mind, you'll be looking for two separate things: building a model over the whole set, and then evaluating the model building approach using cross-validation. Cross-validation is not a model building technique. It is a model evaluation technique. That's why it's listed under test options. Okay, now that we have established that, let's look through some slides to explain all this to you. In class, I started to talk about cross-validation with respect to the play tennis dataset, and I introduced it with the idea that we don't want to train and test on the same data. It's extremely important to guard against subtle ways that we might accidentally cheat and use aspects from our training data, or not from our training data, but from our testing data when we train. When we train, we want to look only at our training data. We don't want to be influenced at all by our test data. And here's the reason why. If we take the model that we train on the training data and evaluate it on the training data, we'll get a performance value. And if we compare that with the performance on the test set, we almost always find that the performance on the test set is lower. The reason is because we have the benefit of perfect knowledge about the training data when we're training, but we don't have perfect knowledge of the test data, and it will be slightly different in its characteristics than the training data, even if it came from the same source. And so what's learned from the training data won't transfer perfectly to the test data, so you will get a performance drop. Now, it's realistic that models that are trained, when you use them, are not operating at the level of performance that you would have observed on the training data. So, since that's going to be the case when the model is being used in practice, then it's a good idea at evaluation time to experience that same drop in performance, so you know what to expect. The purpose of the evaluation is to help you know what to expect when you use that model in practice. So you should keep this in mind. It's very important. If you evaluate the performance of your rule or trained model on the same data that you trained on, you won't get an accurate estimate of how well that model will do on new data. But that's the estimate you want. You want to know what to expect. So what is a cross-validation? Let me explain to you a simple cross-validation. And again, I'm going to lay this out in terms of a 5-fold cross-validation, since that's how we configured the front panel. So what does that mean? Well, if this rectangle on the left-hand side represents our data set, if we're doing a 5-fold cross-validation, the first thing we have to do is divide our data set into 5 segments. We'll refer to the separate segments later, but to get the model that we want to use, we're going to train it on that whole set using all 5 segments. So we're clumping them together, we're training our decision tree, and on the right you see the decision tree that we saw in Weka. Now what we want to know is, how good of performance can we expect to get out of this model? So we can't evaluate this model over the whole set of data because we use that data to train the model. So what can we do actually? If we don't have any other data besides what we trained on, then where is that separate data going to come from that we can evaluate this model on? There isn't separate data. So that means that we can't actually directly evaluate this model. But we want to get an estimate of how well we think this model will perform. So cross-validation is a way that we can estimate how well this model will perform without directly evaluating this specific model. Instead, what we're going to evaluate is the way we built that model. That's what cross-validation does, and it uses these 5 segments of data that we set aside. So now let's look at what that process of cross-validation is. Cross-validation is an iterative process. That means there's a loop, and we're going to go through that loop for the 5 different times. Each time we go through that loop, it's called a fold. So on the first time through that loop, it's called fold 1, and we pick out segment 1 as our test set, and the rest of the data is going to be our training set. So the first thing we're going to do is train on segments 2, 3, 4, and 5 as our training set. And if you look below, you see the tree that we would get if we trained on that data. And then we're going to take that tree and apply it to the test set and see how accurate it is and keep track of that as accuracy 1. Now you'll notice if you look at that tree, it's not the same tree that you saw on the previous slide. It's different. And we expect that because it wasn't trained on exactly the same data. So it's not the same tree, but we built it the same way. We used the same algorithm. We used the same kind of data. We applied it to that data. We got the tree. And now we're applying it to the test set. And the test set was not used during the training. So we can believe the number that we get out, the performance number, because that number isn't cheating. It's not a cheating number because this data we didn't train on it, and so it's unseen data. Now, unfortunately, it's only a small amount of data, so there will be some noise in the estimate of accuracy 1, just because it's not a representative sample of the data, but at least it's a valid test, not a cheating test. Okay, that's fold 1, and now we're going to do fold 2. In fold 2, we pick segment 2 as our test set, so all of the other segments will be our training data. We'll train a tree over the training data. Notice this tree also looks different. It looks different from the tree we built on fold 1. And it also looks different from the tree that we would build over the whole set of data. And yet it's comparable. It's comparable because we use the same algorithm and the data was comparable. It wasn't exactly the same data as from fold 1, but it's very similar. It's coming from the same source. And this is a valid test, this evaluation of accuracy too, because the data that we trained on is different from the data that we tested on. Similar to accuracy 1, it's a noisy estimate because it's only a small amount of data, and so it's not a representative sample, but it has some random noise just like accuracy 1. Okay, fold 3, same deal. Pick out segment 3 as our test set, train on the rest. Notice that the tree again is different. Similarly on fold 4, similarly on fold 5. Now we've seen 6 different trees. We've seen the tree that we would get if we trained over the whole set of data, and we've seen the tree from each of the 5 folds. And we've gotten 5 accuracy values. Each one is going to be different, each one subject to a little bit of random noise because it's a small amount of data. But in each case, the estimate of accuracy is a valid measure of accuracy because there was a separation between the training data and the testing data. Now we will average accuracy 1 through accuracy 5. And that average value is our performance estimate. It's the averaging across the 5 folds allows us to factor out the random noise. So as you average together more estimates of the same abstract quantity, each one with some random noise added in, where the random noise has mean value 0 and standard deviation 1, and we kind of make the assumption that the distribution of noise that's random looks like that. Then as we average, the random noise cancels each other out across these folds. And so the more folds in our cross-validation, the more estimates of the same quantity but with some random noise added in we have, the more the average gets close to the real abstract quantity that we're trying to estimate, because it's less and less and less noise the more and more noise we cancel out. So if that sounded confusing, the important thing here is that what we're doing is we're averaging accuracy 1 through 5 to get an average value, which is the estimate of performance of a model that would have been trained over the whole set of data applied to a separate set of data of the same size drawn from the same distribution. So none of the trees that we built were exactly the same as the tree that's built over the whole data set, and yet each one of the experiments that we ran, 1 per fold, was very analogous. We trained on the same kind of data, we used the same kind of model, and we evaluated it the same way with accuracy. So in some sense, accuracy 1, 2, 3, 4, and 5, they're all estimates of the same thing. They're all approximately this estimate that we're trying to make, which is how well would the tree that we trained first, which was over the whole set of data, do if it was applied to data just like that we haven't seen yet. Because in each case on the folds, we're testing on different data than we trained on. Now, students often find it confusing that it's a different tree on each fold. So then how is it that average accuracy that you get can be associated with yet another very different tree? And the reason is because when we do a cross-validation, what we're really asking is, how good is this method of building a model for this prediction problem? And another way of saying that is, how good are these modeling assumptions? The assumption of what kind of data to use, of what the labels should be, of what the algorithm is. Later we'll talk about settings on that algorithm. So that's a whole set of decisions that were made. How good was that set of decisions? Well, on each one of the folds, the set of decisions was just like the set of decisions when we were applying it to the whole set of data. So if what we're evaluating is the set of decisions, then that's very consistent across all of these tests. And so that's why we believe that when we average together the performance values, that average performance value is a good estimate of how the tree trained over the whole set of data would do on a different set of data. So keep this summary in mind. The model that gets built on each fold is different, but the method for evaluation is the same. Data sampled from the same distribution. The algorithm is the same. We'll call these and other aspects of the approach the modeling assumptions. And what you're really evaluating is the modeling assumptions, not the specific model. So I suggest you say that 10 times fast every morning when you wake up so that you'll remember it. But you can always come back to this video. So remember, cross-validation is an evaluation technique. It's for testing, not for building the model. Some students believe that cross-validation is a way of building a model, that somehow the model you end up with is constructed out of the separate models that are built on each fold. But that's not true. We built that model before we even started the cross-validation. The results that we look at, they come from the cross-validation, but the model itself was built before the cross-validation was done. So cross-validation is an evaluation technique, not a model building technique. And we're going to go through an iterative process throughout the semester where we have a set of modeling assumptions, we run a cross-validation, we look at the results, we may not be happy with them, we adjust our approach, we adjust those modeling assumptions, we run another cross-validation. We keep doing this until we're satisfied with the performance. And when we are, then we'll build the final model that we'll actually use in practice. And we believe that when we build that model, the model's performance will be what we observed when we did the cross-validation. When we use that model in practice. So then we will go ahead and build that model over the whole set. So why do we do cross-validation? We do it when we don't have enough data to divide our data set into two sets. If we had two sets that were as big as the set that we were using in our cross-validation, we could simply build a model over the first half and test it on the second half. And the estimate of performance we get that way should be very similar to what we get when we do a cross-validation over just the first half. But oftentimes, we don't have enough data to make that practical. If we divided the data we have in half, then the amount of data that we would train on would be too small. We want to be able to train on a much bigger set. If we do cross-validation, then on every fold, we're using most of the data we have for training. And so it works out better when you have a small set of data. What we're trying to do is estimate what performance we would get if we trained over the whole set of data and then applied that model to an independent set of data drawn from the same distribution and of the same size. We compute that estimate by computing first the accuracy on each fold and then averaging across those. And the averaging allows us to cancel out the noise in the estimate from each fold, as we pointed out earlier on. Now, I keep talking about estimating the performance accuracy, but actually any of the performance metrics that we have talked about could be used in place of accuracy. Now, sometimes students ask, do I actually have to do all of the folds? Why couldn't I just do one? Well, we did talk about how it is that the test sets on each fold, they're usually pretty small. And so, therefore, like I said, the performance estimate on each fold is noisy. The noise will be canceled out when we do the averaging across folds, but we really need all the folds then. We shouldn't stop before we've run the entire cross-validation. So what are the advantages of cross-validation? Well, it makes the most of our data because on every fold we use the largest portion for training. So we can get away with the smaller data set. And we have a great advantage then from cross-validation if we don't have enough data to do just a train set and a test set. And on every fold, we have avoided training and testing on the same data, so it allows us to get a valid estimate of our performance, one that's not an overestimate. If we train and test on the same data, it always gives us an inflated result. But what we have to keep in mind is that if we go through this iterative process, as we will, throughout the whole semester, even if we never cheat and look very closely at the data that we're testing on, we get to know our data from the results on the experiments, even if we get to know it sort of indirectly. And so we're going to have to think about ways of being careful and guarding against what we're calling overfitting in the practices around management of our data set that we'll talk about after this video. This video is really specifically about cross-validation. So now you have the basics of cross-validation down. Later in the semester, we'll talk about more advanced aspects of cross-validation. So hopefully you can absorb all this now and ask all your questions so that you'll be ready when that time comes. And I wish you the best of luck.